Modern life works because of satellites. They give you internet, GPS, music streaming, news, and the ability to communicate with your family and friends anywhere at any time. But those satellites are always at risk because they don't operate in a calm space. They operate inside of a constant stream of charged particles and magnetic fields flowing outward from the sun. We don't live next to a star, we live inside of it. When we picture space, we usually imagine it as quiet and empty, with the sun far away just sort of doing its own thing. But physically, that's not how space works. The sun doesn't stop at its visible surface. It has an outer atmosphere made of charged particles, so hot they escape the sun's gravity and flow outward in all directions. As those particles move, they carry the sun's magnetic fields with them. And this outflow never stops. It continues every moment of every day, filling the space between planets.
And this isn't just sunlight and heat. It's matter, it's real particles. They're carrying energy, momentum, and magnetic fields as they move. So when we talk about the environment around Earth, we're really referring to the environment that's created by the sun itself around the planet. And Earth and everything else that we know in our solar system sits firmly inside of that flow of charged particles from the sun.
Once you're inside this environment, the question becomes what it actually does to the things moving through it. The charged particles flowing outward from the sun aren't drifting lazily through space. They're moving fast, hundreds of kilometers per second, and because they carry electric charge, they don't move independently. The plasma flow carries the sun's magnetic field with it, interacting with other magnetic fields along the way. The continuous plasma flow, known as the solar wind, forms in the sun's outer atmosphere and it streams outward through the solar system. When it reaches Earth, it runs directly into Earth's magnetic field and it's forced to flow around it before continuing on through the solar system. This process of running into and flowing around Earth's magnetic field leads directly to the formation of what space physicists call the magnetosphere. This isn't a clean process. There are many cascading effects, and over short periods of time, on the order of hours or days, they can lead to significant reorganization of the system as a whole. Earth's magnetosphere acts like a shield against the solar wind, but it isn't a fixed shield. It moves and bends and it gets reconfigured. When the solar wind hits it, the field compresses on the side facing the sun, we call it the day side, and it stretches out on the night side, forming a long magnetic tail that extends much further beyond Earth. We call this the magnetotail. This process of stretching and compressing stores energy in the magnetic field itself. As charged particles encounter Earth's magnetic field, they don't move in straight lines. They spiral around magnetic field lines. They get guided, redirected, and in some cases they get trapped on those field lines. Instead of passing straight through, particles can be forced into these looping paths that keep them circulating around Earth for long periods of time. This is how energetic structure forms in the space around Earth. Regions develop where magnetic field lines guide incoming particles from the sun, allowing energy to accumulate and persist. It's similar to how a river forms whirlpools and eddies behind rocks. Most of that water keeps flowing downstream, but some of the regions trap motion and energy for longer periods of time.
That's what's happening as the solar wind encounters objects like planets, other magnetic fields, and even existing particle populations. The overall flow continues, but localized structures can build up where energy can accumulate. And then when a disturbed or energized region of solar wind comes through that area, these structures can be broken down and then get reorganized very quickly.
It's like a sudden surge entering that river. With enough new water and momentum, they will wash out the existing eddies and redistribute the flow. In the magnetosphere, energy that was stored gets released, causing currents to intensify and particle populations to be rearranged. These transient disturbed states and the cascading effects that they trigger are what we refer to as space weather. Well-known examples include solar flares and coronal mass ejections at the sun, and effects closer to Earth like auroras, which occur when those disturbances interact with our atmosphere and our magnetic field. Satellites orbit directly inside this continuous particle flow. As they move through this environment, they cut across magnetic field lines and charged particle populations. These interactions lead to surface charging, which is an accumulation of electrical charge on the different parts of the spacecraft, and this can be a serious problem if they're not mitigated. Surfaces charge and discharge, instruments are exposed to energetic particles, and materials degrade under the constant bombardment. Over months and years, those effects become mission limiting. And this environment's not steady in time either. When conditions at the sun change, such as when solar wind speeds up or slows down, or it becomes more turbulent, the structure of near-Earth space changes with it. Earth's magnetic field can be rapidly distorted, releasing large reservoirs of stored energy into the magnetosphere. And when that happens, particles are injected into regions they don't normally occupy. Currents in near-Earth space intensify and radiation levels often spike. From a physics standpoint, this is considered active coupling between our planet and its host star. Earth's magnetic field is continuously coupled to the sun through this flowing plasma, the solar wind. Changes at the sun propagate outward and physically reshape the space around Earth. Satellites and astronauts experience those changes as real conditions that they must survive. This is the operating environment of near-Earth space. All of this means that satellites aren't just orbiting Earth, they're operating inside of a living, moving system that never shuts off. Every signal that we rely on, such as GPS timing, navigation, communication, data transfer, it has to pass through this environment. Those signals don't travel through empty space either. They move through plasma that's threaded with magnetic fields, and when that environment changes, the signals can no longer pass through it the same way.
Timing protocols can shift, orbital paths become hazardous, and positions of the satellites themselves can even begin to drift off course. Modern systems are only able to operate in this environment because there are teams of mission operators and scientists around the world who study the physical conditions around these spacecraft in real time, and they can make adjustments accordingly.
And this matters more than most people may realize. GPS isn't just about directions on your phone. It underpins financial transactions, network synchronization, emergency response, shipping logistics, aviation, and even defense industry activities. Small timing errors can cascade into real-world disasters and disruptions fast. The reason those systems feel seamless is because an enormous amount of effort goes into understanding and compensating for the space environment that they operate in. Satellite systems require continuous real-time monitoring and adjustment. Orbits are planned far in advance and they're tracked with every single orbit. Clocks have to be adjusted and models have to be updated. Mission specialists assume conditions will change, because they always do. While many parts of our system are automated, they aren't designed to operate fully autonomously. They have to survive inside of a hostile environment that is constantly changing from threatening to deadly. Astronauts live with this reality even more directly. Radiation exposure levels aren't steady and continuous. It depends on what the sun is doing. Missions are planned around periods of lower activity, and spacewalks are scheduled with space weather in mind. Closer to the surface, flights can be delayed, shortened, or canceled entirely when conditions become unsafe. Human presence in space only works because we understand that this environment is dangerous and highly dynamic, and that we plan accordingly. Even here on the ground, we're not isolated from what's happening above us. Power grids can be affected when strong currents are induced in the Earth during intense space weather events. During these events that we call ground-induced currents, powerful currents can be generated along pipelines, power lines, underground cables, and even railroad tracks. Any transformers or power stations along the way are typically damaged as a result. Long-distance radio communication can quickly degrade as well. Sometimes it can fail altogether. Aviation routes are diverted from certain regions when radiation levels and communication reliability change. This happens most often near our poles, where the configuration of Earth's magnetic field allows more solar wind to reach closer to the surface than anywhere else. Navigation systems that rely on precise timing can easily malfunction when the space environment becomes more disturbed. And this can be an inconvenience or a tragedy depending on what is being driven off course, even by a few meters in some cases. I've spent a lot of years traveling, sometimes far from home and sometimes in places where a communication infrastructure just isn't guaranteed. One thing that's always made those moments easier for me is knowing that I can communicate with friends and family back home. That connection changes how safe and grounded I feel sometimes. When it's threatened, that comfort can go away with it. In many parts of the world, access to the internet isn't just a convenience for doom scrolling. It's the primary way that people learn and connect and understand what's happening around them. All of that depends on systems orbiting inside of a hostile and changing environment. That's why scientists and engineers are constantly monitoring the sun, modeling space weather, and designing systems that can adapt, recover, and keep working even when conditions around Earth become unstable. It's also one benefit of satellite constellations. redundancy, helping to ensure continued operations at large.
Modern life is possible because we've begun adapting to the environment that's created 93 million miles away by our host star. And when we consider that, the takeaway becomes fairly simple. Space is not just a backdrop. It's an active environment that shapes what's possible above our planet. And the more that we rely on systems that are in orbit, the more that it also shapes what's possible here on the surface as well. As we place more infrastructure in orbit and we rely on it more heavily, it becomes less of an option for us to understand this environment. And that brings us to a deeper question. If Earth sits fully inside of the atmosphere of the Sun, then where does space actually begin? Is there a clear boundary at all, or is it just a gradual change in the physical conditions the further away from the surface that you get? That's what we're going to look at next. Thanks for hanging out. Cheers.